There's this whole set of numbers that people call imaginary, but what if I told you they're absolutely essential for describing the real world? Well, today we're going to master complex numbers and see exactly how they make the impossible possible.
So, for literally centuries, this one little question was a total roadblock for mathematicians. I mean, you can't take the square root of a negative number, right? Not with the numbers you and I use every day. Well, that's exactly where our story kicks off.
So, what do you do when a problem seems impossible? You get creative and you invent a solution. Mathematicians just defined a new number. They called it I, and they gave it one simple, elegant rule. I squared equals -1. And just like that, a whole new dimension of math opened up, where every number has two parts, a real part, A, and an imaginary part, BI.
Okay, so how do we actually use these new numbers? Let's start with the easy stuff, adding and subtracting. And the good news? If you've ever done any basic algebra, this is going to feel super familiar.
The main idea here is to treat them like different types of things. You add your apples to your apples and your oranges to your oranges. You don't mix them up. It's exactly the same here. You just combine the real parts together and you combine the imaginary parts together. Simple as that.
Let's look at a quick example. We've got two complex numbers here. So we'll take the real parts, 5 plus 2, which gives us 7. Then we take the imaginary parts, 3i plus 7i, and that gives us 10i. Slap them together and our answer is 7 plus 10i. See? It's really that straightforward. All right, now for multiplication. This is where things get really fun because it's the first time the real and imaginary worlds actually get to mix. And it all comes down to that one special rule we learned about, I. And the great thing is, the process itself is nothing you haven't seen before. If you remember using the FOIL method from algebra class, first, outer, inner, last, you're already set. You've got all the skills you need.
We just follow the steps. We multiply the first terms, then the outer terms, then the inner terms, and finally, the last terms. And pay attention to that last step, because that's where the magic really happens.
And this is it. This is the whole key to the puzzle. That last step gives us an I squared. And you always have to remember this twist. I squared isn't just a variable you leave hanging around. Nope. It's like a switch. The second you see it, it transforms into the real number -1. So we just swap that I squared for a -1. Our 10i squared instantly becomes a real number, -10. And now look, we can combine our real parts, 12 and -10, and we can combine our I parts. That gives us our final clean answer, 2 plus 23i. Okay, on to what a lot of people think is the trickiest operation, division. But don't worry, we've got a secret weapon that basically turns this whole problem into another multiplication problem we already know how to solve. Just like in algebra, when they tell you not to leave a square root in the denominator, we have a very similar rule here. The number one goal is you just can't have an I down there. We got to get rid of it. And this is our secret weapon. It's called the complex conjugate. And it sounds fancy, but it is so easy to find. All you do is take your complex number and you flip the sign in the middle, the sign right in front of the imaginary part. That's it. And here's why it's pure magic. When you multiply any complex number by its conjugate, the middle terms with I in them always cancel each other out, and that I squared at the end turns into a real number. It's a trick that guarantees you'll be left with nothing but a plain old real number in the denominator every single time. So the game plan is pretty simple. Step 1, find the conjugate of the bottom number. Step 2, multiply both the top and the bottom of your fraction by that conjugate. This way, the value doesn't change. Now all you have are two multiplication problems, and you can bet that the I in the denominator will just vanish.
So beyond the basic operations, I has another really cool property. It's this beautiful, surprisingly simple pattern that pops up when you raise it to different powers. And once you see it, calculating huge exponents becomes ridiculously easy.
Let's just watch this pattern unfold. So I to the power of 1 is, well, it's just I. Easy enough. Next up, I squared. We know this one. It's our fundamental rule. -1. Now, I cubed is just our last result, -1, multiplied by I again. So that gives us -I. And for I to the fourth, think of it as I squared times I squared. That's -1 times -1, which brings us all the way back to +1. And boom, the cycle starts over. I to the fifth would just be I again. So here's the shortcut for any power of I, no matter how huge. Just take the exponent,
Divide it by 4 and see what the remainder is. That remainder, whether it's 1, 2, 3, or 0, tells you exactly where you are in that simple 4-step cycle. It repeats forever.
So you might be thinking, okay, this is a neat math trick, but why does any of it actually matter? Well, it turns out these imaginary numbers are the perfect language for describing all sorts of real-world stuff. They're all over electrical engineering, signal processing for your phone and Wi-Fi, and even deep in quantum mechanics. They're not just some math curiosity, they're a fundamental tool for how we understand the world.
Okay, let's pull it all together real quick. Remember, we treat real and imaginary parts separately when we add, but we let them mix when we multiply, all thanks to that golden rule, I squared equals -1. We've got our secret weapon, the conjugate, to handle division, and we know that the powers of I just keep dancing in that predictable 4-step cycle. It's kind of amazing to think about, isn't it? Just by daring to solve one impossible problem, the square root of -1, we unlocked this whole mathematical language that literally powers our modern world. It really makes you wonder, what other incredible breakthroughs are just waiting for us, hiding inside the next impossible problem?